Okay, so in this video, I'll be going over a sample problem from the kind of the introductory material on fluid element kinematics in Chapter 6. The problem is 6.8, but before I get to there, I just want to show a diagram from an old version of the book and then the associated diagram of a new version, the new version of the book. But to kind of motivate this problem and why it was chosen for this video, and it was chosen because it introduces the ideas to all of these different ways that the fluid element can move about in space and be deformed in time. And so I prefer this old version of the diagram, and I'll show you the new version, and I'll discuss both of them here. But the idea here is that at some instant in time, a fluid element, a small little infinitesimally small element of our fluid is given by this black line, and then later in time it's evolved to be this shape, and by evolving into that shape, it shows all the different ways that the element can change. First, it can translate in space, all right? And that translation is given by our velocity vector, let's say, right? So then the change in x is just the x component of velocity multiplied by the small time step. The vertical change here is the v component, or the y component of velocity v, multiplied by the small time change, gives us the change in space in the vertical direction here. So that should be the most common sense thing that can happen to a fluid element. It can just move, right? While at the same time, it can also deform in different ways. Well, I guess maybe we'll just skip over to here. The other way it can move without deforming is it can rotate, right? You see the shape itself hasn't changed, but just the rotation brings it to this new shape here, right? So we get movement from the velocity vector. The rotation is then measured by what we call vorticity. Now the book calls vorticity, let's see if I get this right. Okay, so what I'm used to is this omega vector is vorticity, defined to be the cross product of the velocity vector. I think the notation in the book is that vorticity is actually still the cross product of velocity, but omega is when it's a half. Okay, so it's just the differences of a factor of 2 here and there, but essentially a measure of vorticity is the cross product of velocity, and usually that's given the symbol omega. It's a vector. I think in the book it has a Greek symbol for a different Greek symbol for actually vorticity, but and that tells us about the rotation. The curl operator it always takes the rotational aspects of whatever vector field you're talking about, and you get that. So just like our velocity has components u and v in just this 2D space, in the 2D space, if you work through it, the only rotational elements you can get are the z component of vorticity, or the z component of this omega vector, this rotation vector. And so what that means is that the axis coming out of the page is your z-axis, and along that axis is where we're getting rotation, right? So that's your thumb for the right-hand rule. And you can't get any, if this is really a 2D element, you can't get rotation in the other, along the x or the y axes. The other way that we can get, I'm sorry, so now we have translation and rotation. Those are ways to move and rotate our shape without changing it. And then we can also, the object can deform in time as well. And so the linear deformation basically means we can shrink or expand in any of our component directions. Okay, so you can think about this as due to normal forces on the surface of our element, right? Well, this has come out with the volumetric dilatation rate is how we measure the linear deformation. So that's the divergence of velocity, or, which in 2D is just du dx plus dv dy. Okay, and then the last way that an element can change is through straining, shear straining. Right, so this should look familiar. This is just a pure angular deformation coming from the straining of in a shear fashion. The shear strain. Yeah, I'll add that here. This is really limited to shear strain rate. Okay, Shear strain rate, it's a rate of change because we're talking about a fluid element, so that's why it has a dot on the top. It's a time rate of change of our shear strain. Okay, in 2D, this is just now dV dx plus du dy, where the vorticity was dV dx minus du dy. All right, so you get your cross derivatives here for this bit, and then the linear deformation is the sum of all of the derivatives in their own, the derivatives of velocity in that same component direction gives you your divergence. Okay, so those are the different ways, a general way an element can change in a small time step. It can translate, given by the velocity vector. It can linearly deform from the divergence of the velocity vector, or the dilatation. It can rotate from the curl of the velocity vector through the vorticity, and it can also deform angularly. We can get angular deformation from the shear strain rate, which is the sum of the cross derivatives. Let's see here. So now this is the image you'll find in your book now, and again you see the same things. We have, and they're basically saying the same thing. I just think this is less powerful. But we have general change. The general motion here is given. A particle starts here with this shape, and at some later time it's moved to here with a different shape, and that comes from translation through the velocity vector, rotation from. So see, this is why I don't like it, because rotation alone doesn't translate, just the translation does. But maybe they're saying once we've translated it, then also rotates. All right, so rotation gets a new orientation. Linear deformation, it can shrink in this direction, it's expanding in the other direction. That's all linear deformation. And angular deformation gets that shearing look to it. Okay, so getting to our problem, I think I spent more time on that than I thought I would. Here's the sample problem. It's 6.8. And what we have is, for this linear velocity distribution that's produced by having a layer of fluid, a layer of a viscous fluid between two plates, and then pulling the top one while fixing the bottom one, we get this linear velocity distribution. And this comes from, I mean, we've seen this before back in chapter 1 when we were introducing the idea of viscosity. Okay, so if this is an incompressible fluid, kind of a key here to part A, let's determine some of these. Basically what we're going to do is, well, we're given the velocity field, so we already know how elements translate, right? So the velocity field is just, here's our u component of velocity, and our v component is just 0. Right? So that tells us a bit about the translation, just given in the problem statement, how fluid elements translate in time. But in terms of the other three, we need to do some calculations. So the first part says, let's determine the volumetric dilatation rate. This is a measure of the volume change for fluid elements in the flow. That is the divergence of velocity, where we're just taking du dx plus dv dy plus dw dz if we're a three-dimensional flow. Well, if we look at well, first of all, v and w, there's no v and w. Those are just defined to be 0, so those are both 0. But then du dx, if we look at u is just a function of y, so that's also 0. So it's pretty trivial, 0, 0, 0. Yeah, the sum of those are just 0, which is good, because we were told this is an incompressible fluid. Incompressible fluids must have 0 divergence of velocity. It's actually another way to define what we mean by an incompressible flow. Okay, so an incompressible fluid is where density is impossible. A true incompressible fluid is where density is impossible to change. Right? It's impossible to change the density of an incompressible fluid. An incompressible flow has this true, right? Or a flow that's not compressing has the divergence of velocity equal to 0. Okay, that doesn't mean that this can't happen. This can still happen, where we have shrinking in one direction, expanding in the other. It's just they must be done at the exact same rate, such that the volume doesn't change for an incompressible fluid. All right, second one, rotation vector. That's going to make a statement about our rotation. So our rotation vector is this omega, and then vorticity is where we've taken off the half factor, so we multiply it by 2. And that's parts B and C, which we'll do at the same time here. So our rotation vector is a measure of angular motion, it's rotation, and also, vorticity is then therefore also a measure of rotation in the flow. But let's just start with the rotation vector. That's defined to be 1/2 of the curl of velocity. We take the curl here, I, j, k components, all the derivatives, and then each of the velocity components here. We see for the I component, that's just going to be 0 minus 0. For the j component, that's 0 minus, that's 0 minus the derivative of this guy with respect to z. Well, this is not a function of z, so that's also going to be 0. And then for the k component, that's 0 minus now the du dy of our u component of velocity. That is a function of y. Its derivative is just big U over b. Therefore, we do have a non-zero rotation vector. And we just have the k component. Again, this is a 2D flow we're talking about here. Actually, it's a 1D flow, but changes in y, so it's really a 2D flow. So we only get rotation in our along the component coming out of the page here. And the negative sign means that we get, so this would be a positive sign, but negative means your thumb actually points down, and you get rotation in a clockwise sense, and that's what the fluid elements experience. And you kind of see that, right? If a particle is originally a square, right, and its top part of the square would have a faster velocity than the bottom part, it's going to overturn in this way, right? As the fluid goes, it's going to turn, 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 turn. Okay? In a clockwise sense. The vorticity is just then 2 times this rotation vector. And so it's truly just the curl of velocity without the half factor. And that's why we have a 2 on the bottom there. So we just get rid of that 2, or multiply through by 2. And this tells us that this is a rotational flow. Irrotational flow has 0 rotation vector. It has 0 curl of velocity. So this must be a rotational flow. All right, and so then now we've talked about, well, our problem statement tells us about the velocity vector, the translation of our fluid elements. Our volumetric dilatation rate tells us about the linear deformation. We then, the rotation vector and vorticity tell us about the rotation of a fluid element. Let's now talk about the angular deformation. And that comes from the shear strain rate, right? So the shear strain rate in 2D is just it's the rate of shear straining. It's just dV dx plus du dy. Well, v is 0, and so therefore obviously it doesn't have a change in x, so that's 0. But du dy, we've actually already calculated, it's just u over b. And so therefore our shear strain rate is u over b. So we do get shear straining. So as our fluid element translates along in the u direction, depending on where it is, it's not changing its shape, right? The square keeps its shape in a linear sense. Basically its volume isn't changing, but it's rotating and shearing at the same time. Okay, so an element that would originally start here moves along in the x direction because it has u velocity, so it translates, rotates in this clockwise sense while having a shear strain. Okay, and then the further it goes along, the bigger your delta t, the more rotation you get and the more shear straining you get, more angular deformation. Okay, so it's a nice little sample problem. The actual calculations aren't complicated, and if you're just paying attention to the definitions of these things, that's easy. But I think that getting a true appreciation for what these things are measuring is what's more important from this sample problem. All right.